All right, so what we are going to do today is talk a little bit about allostery and its importance in physiologic processes. And the reason why I chose this topic is because allostery is becoming more and more important, especially for GAGs, okay? Especially for the types of molecules that we are interested in. And it's a process for regulation, right? And obviously we are interested in GAG-mediated regulation of a number of processes, coagulation, for example, inflammation, and going forward, hopefully angiogenesis, cancer, and things of that sort. So allostery is so allostery is a really fundamental process that we can actually exploit, which is the reason I think I would like to have a discussion about this particular topic and hopefully impress upon you that this is a beautiful mechanism to exploit in terms of design, in terms of mechanism, things of that sort. So let's start with really the basics as to what allostery is all about. Some of you might have taken this concept some time ago, so I do have a refresher. So what is allostery? Allostery is a process that essentially arises from the coupling of a molecule that we would like to call as the effector ligand. It's a molecule that induces an effect at a site which is remote from its primary site, right? Which is why we use the word allos, site arising from stereo, from the primary ligand site, so as to induce some structural and or dynamic changes that essentially result in regulation of the binding of the primary ligand. So in essence, we have the definition itself conveys two sites. You had to have two sites. The primary site, for many of us, we typically use enzymes. So the primary site, as far as enzymes are concerned, is going to be the active site, right? Is going to be the site where catalysis happens. So that's our primary site as far as enzymes are concerned. Doesn't have to be restricted to enzymes. It can essentially be any protein. It can be receptors. In the field of receptors, this is even more common. But the reason why we would like to obviously discuss is because our focus is coagulation enzymes, for example, and even for single chain enzymes, polypeptides, we see this effect more and more. So allostery has been was described a long time ago, and this is a figure that you are going to see quite a lot, not just in today's talk, but over what literature reports. For most part, and this is probably 15 years ago, 10, 15 years ago, allostery was essentially thought of as something that relates to several different subunits and the way that they interact in a given protein. And that's what allostery was thought about for most part. So here I'm showing you, this is a classic case of hemoglobin. So here I'm showing you, for example, the 4 subunits of hemoglobin binding its ligand, which is oxygen, and inducing a change in one of the subunits. And that catalyzes, for example, change in other subunits, so more oxygen binds so that we get a fully saturated, oxygen saturated hemoglobin tetramer, right, 4 subunits. So in essence, for most part, the reason why this was thought about as this we classify as allosteric is primarily because binding of one makes the second oxygen bind better, which makes the third oxygen bind even better, which makes the fourth oxygen bind even better. So there is some kind of coupling, which is why we use the word coupling. These are not independent. That's what it essentially means. Okay? So this is the fundamental definition of allostery. When the phenomena of oxygen's binding to hemoglobin was discovered, in terms of quantified, at that time it wasn't really defined as allostery. So in terms of discovery, 1903, the sigmoidal binding curve of hemoglobin binding to oxygen was described. So under the characteristic binding phenomena is when a molecule, when a substrate or a ligand binds to its target, a macromolecule, and you plot the response in some fashion. If you have a response, changes in the protein function, whatever that is. So when you describe this in terms of the substrate concentration, simply substrate concentration, not log substrate concentration. Okay? So this is a linear scale. When you describe this in terms of a linear scale, under normal conditions, when there is no allostery, the profile essentially looks like this. What is this profile? What is the name for this profile that you all know of? This is characteristic. I think all of you know this, right? What is this profile? Okay, so just to refresh. So when we forget about myoglobin, I'm simply saying a protein for which you describe percent response, functional response, or most commonly saturation of the protein by the ligand, which is what you are plotting, on a linear scale, and you get something like this. You have seen this quite a lot. You have seen this for enzymes, you have seen this for receptors, you have seen it for so many. What is the name of that profile? If that is difficult, what is the function that you could fit it to that profile? Mathematical function. The hyperbola, right? This is a rectangular hyperbola. This is a rectangular hyperbola. The mathematical function is essentially this without the n, or n is equal to 1. That's the rectangular hyperbola. Okay? Without the n, or n is equal to 1. So under normal conditions, so once again to repeat, because many times you will see in literature profiles of this sort, which is what is called sigmoidal binding curve, okay, like a sigma-like. So, but that doesn't automatically mean it's allostery, which is what I'm trying to tell you. And this is simply an alert, because then you have to look at what scale is it. Okay. If it is a linear scale and you get a sigmoidal profile, then chances are it is allosteric. If this scale is a log scale, you will convert that rectangular hyperbola into a sigmoidal scale, into a sigmoidal profile. So that's an alert. So when you are interpreting literature, you have to be cognizant of what type of scale is it. Okay. Other than that, on a linear scale, when you're simply plotting percent saturation or whatever response that you are measuring, which corresponds to how much of the complex is found, is formed, and you plot it on a linear scale, and you get this sigmoidal profile, then most probably it is allosteric process. Okay, most probably it is allosteric process. Additional things have to be done to confirm that this is allosteric. So, hemoglobin binding to oxygen displays that kind of a profile. Okay, and that has phenomenal advantage. That has some major advantages. Myoglobin, on the other hand, myoglobin is a monomeric unit, fairly similar to hemoglobin. It has a single heme. Likewise, hemoglobin has 4 subunits, 4 hemes. Each of the hemes bind an oxygen. Right? You have a question? Okay. Each of the hemes bind an oxygen. So, under the conditions where you have 4 subunits, what does this mean? Physically, what does this mean? When you have a sigmoidal profile on a linear scale, what does that mean? That really means that at low concentrations of oxygen, the change in response is slow. That means it is getting saturated, but not at the rate that it should under normal conditions, when there is no cooperativity. The first few oxygens that are binding to hemoglobin are binding with a lower affinity, resulting in the percent saturation much slower than what would be normally expected. Then what happens is, as the concentration increases, you see a sudden jump. Between this concentration, you have a phenomenal jump in saturation, right? Significant increase in saturation. So what happens therefore, and this is good for regulation. When the need arises, for example, when the concentrations in our bloodstream go down, oxygen is released to the system so that it can be very useful. So this is beautiful part of regulation. And obviously at very high concentrations, you reach saturation, which is similar to what you should typically get. Okay? So this kind of a profile is sigmoidal profile. And in 1910, Archibald Hill formulated an equation to describe this profile. And that is this equation. And this is something that you might have seen. This is something that you might have seen quite a lot. And you might have also heard about N being the Hill coefficient. So it's actually coming from this profile, right? So the concentration of ligand raised to the power N, concentration of ligand raised to the power N, dissociation constant theta is essentially the fraction of bound hemoglobin. How much of the complex is actually formed. So this is a fraction or percent, whatever that you want to define. And this is Hill coefficient. It's actually a measure of cooperativity. For most part, the simplest interpretation is, what is this slope? Right? For most part, what is that slope? How fast does it rise? How fast does it go up? Is this indicating? So in physical sense, when you actually see a profile, you don't even have to know N, the value, in order to interpret the level of cooperativity. You can actually see this, and if this is really, really steep, you effectively get some idea about what is the cooperativity. Okay? Now, obviously, as I said, this phenomenon was not labeled as allostery at that time. This was simply described, and the equation was put forward, and they said, okay, this is a good way to understand, and this is a good way to explain this particular process. The word allostery came much later on. Okay, so here's the origin, essentially, origin of the word allostery. And so there were several things that were going on at that time, and people were trying to understand how amino acids are biosynthesized. So the amino acid biosynthesis was being discussed quite a lot, and there are several enzymes that are involved in, for example, the biosynthesis of tryptophan, starting with chorismate. And this actually serves as a precursor for several different other enzymes, but I'm simply describing this. This was one of the major points where the idea about allostery arose. So what happens in real life is that chorismate is converted into anthranilate, which in several steps is converted into a molecule which is a precursor to tryptophan. And what was being noticed was that after the synthesis of this, tryptophan would inhibit. When the concentrations of tryptophan reached a certain level, it would start inhibiting an enzyme which was somewhere in the initial stage. In this particular case, anthranilate synthase. So this was being described as feedback inhibition, right? You are feeding back, and this is very common. So now, once again, you might know of this process because this is fairly common. Once again, this is a regulatory feature. You don't want a buildup of tryptophan to significantly higher levels. So in essence, therefore, this nature has engineered this entire process so that it restricts too much synthesis of tryptophan. But then people started thinking about, and this also happens for several other, for example, amino acids. So one of them is valine. So valine is synthesized from pyruvate, and what happens is that valine inhibits acetohydroxy acid synthase, which is that particular enzyme. Also happens for isoleucine, also happens for leucine. So leucine inhibits its enzyme right before it's made. So in essence, this is fairly common, okay? And so people started thinking about, so how do you explain this phenomenon? Why is it that this particular molecule is inhibiting the reaction in which this molecule, looking at the structure, this molecule has nothing to do, in terms of similarity, has nothing to do with that particular molecule, right? How does that happen? So then came the concept that, well, this molecule must be binding this enzyme at a site which is different from the site that recognizes this structure. Right? So because the structures are different, they must be binding somewhere else. That's the introduction of the word allos, right? And site, steric. So there's a beautiful, I forgot that, there's a nice paper that just got published, I think it's 2011 or 2012, that talks about the origin of the word allostery. It's by Chajon, and he really goes into the detailed discussion about, who said what, and it's a nice historical read. Tells you a lot about, how the words are put together. So I think I forgot to write here. So in 1961, after a lot of discussion, Monod and Jacob proposed allosteric inhibition to the NSU effect. So this was the effect. The NSU effect was this. Feedback inhibition was NSU effect. Okay. So they proposed the term allosteric inhibition. And then in 65, Monod, Wyman, and Chajon proposed a model of the concerted allosteric transition, which is even today recognized as the MWC model. Okay? This is a model which is even today is recognized. And once again, here's a description of what the model means to hemoglobin. Okay? To hemoglobin. So here, for example, is hemoglobin. Typically, hemoglobin is these days described in essentially two states. One is T, which is tensed, and one is R, which is relaxed. Okay? You can describe these in any different forms: relaxed, tense, state 1, state 2, whatever. So in essence, what the model says is that the tense state and the relaxed state are in equilibrium. And then oxygen can bind either of these states and then move it in either direction. But because the affinity of oxygen to the relaxed state, one of the states, is higher and it progressively increases, that you end up with this kind of a unit. Okay? This is a concerted mechanism. Okay? What does the word concerted mean? The word concerted simply means happening together, okay? Happening in sync, happening simultaneously. That's what the word concerted means. To put it into physical perspective, this essentially means, if you look carefully, let's just first look at the generic two-state model. So rather than thinking about 4 states, it's a little bigger system. You can think about 2 states. And in actuality, you can actually think about single polypeptide chain also. But this doesn't have another ligand. And we want to move in the direction of actually 2 ligands, right? Oxygen is just 1 ligand as far as hemoglobin is concerned, which is what I want to introduce L. So here we have a substrate, for example, an enzyme. So we have a substrate and a ligand. So we have a tense state and a relaxed state. Binding of the ligand changes that state into this state. But notice what we are invoking here is that when the ligand binds, we can imagine that the ligand would bind to this subunit or that subunit. Because there are 2 subunits, and then therefore hopefully there are 2 binding sites, the dissociation constant would double, right, because of the stoichiometric effect. But binding to either changes both. That's what I'm trying to invoke here, right? Binding to either changes both. Binding to either changes both. Binding to either changes both. So that's concerted. That's what I mean by concerted, happening simultaneously. Both of these things are happening simultaneously. Inherent in it is that, I don't write the word here, inherent in it is this is symmetric, okay, which essentially means that these 2 states, there are symmetry. Symmetry is preserved. That was the model, okay? That doesn't mean that this model is the final model, but that was a model. And in essence, therefore, eventually you end up with RS2, okay? So inherent, there is a symmetry here too. For example, you can think about, so this is one way in which you can think about where binding to one converts all into, all 4 are modified. All 4 subunits are modified. You can think about symmetry being maintained with just 2 subunits. You don't have to have 4. For example, these 2 could be modified and you would still maintain symmetry. There would be a mirror image symmetry here. Or you could modify this and this, and they would still be symmetrical. So you can have several different mechanisms of how these things could work. But in essence, MWC model is a concerted model. Things happen so that appropriate symmetry is maintained. And that's important, primarily because if there is symmetry, then for most part the affinities can change in a certain fashion, right? So, so a few years later, Koshland, Nemethy, and Filmer proposed a sequential model. So you don't really have to have symmetry. And this is also true for hemoglobin, because hemoglobin, so just going back, so in essence, if the model was complete transition or 2 at a time with symmetric, then the first oxygen would have an affinity which is similar to the second oxygen, right? Because you have symmetric transition, and the structures would therefore remain the same. And therefore, if at all, under certain conditions, you would have all affinities same. Okay. Now, that was not the observation for hemoglobin, and therefore they proposed that it doesn't have to be all at once model. It can take in a stepwise manner. So you can go 1 step at a time. When you go 1 step at a time, there is a clear possibility of destroying symmetry. So what might happen is that binding of oxygen to one of the subunits changes the structure of that subunit into essentially a final form. That's our final form, right? However, the binding here induces some structural change in other subunits that makes it more conducive to recognize the second oxygen. And when this binds, there could be a change in this followed by complete conversion into the final state. So you can imagine that there would be a gradual progression in the affinity of the oxygens coming in, right? Conceptually, you can imagine. Is this clear? Yeah, go ahead.
How do you decide the symmetry? Do you need a crystal structure, or how do you know that it's like C2 symmetry or there is a sigma plant in that hemoglobin?
Yeah, I mean, now we know a lot about hemoglobin.
It's like 1965 or 1966.
But this is a model that was proposed.
So it's a hypothesis.
Yeah, it was a hypothesis at that time, and a very logical one, that, you know, this is what it is. The other thing is that you don't really have to have crystal structures. At that time, you don't really have to have crystal structures. Why? Because a lot of biochemical experiments were being performed. And you can actually measure the affinity of these individual oxygen. I have a slide that's coming up pretty soon that shows what the affinities in the sense the partial pressures are. Okay, so yeah, absolutely. But for today, for us, in order to prove allostery to the level that is possible with hemoglobin, I don't really know. It's extremely difficult, and you will see why it is, because allostery has gone a dramatic change in thinking in terms of what allostery is. Okay, so bear with me. Okay, all right. So the Hill equation actually can be derived very simply, and I have a question at the end, so be prepared. Okay, so the Hill equation can be derived very easily. Okay, extremely easily. I mean, there is nothing, no big deal. So if we take hemoglobin plus 4 oxygens, and the 4 oxygens bind to hemoglobin, this is the equation that we are dealing with, right? That's the equation. So in essence, if we write bound versus total, which is the fraction bound, right? That's what the fraction is. That's actually theta. So if we write bound versus total, what is the bound? Bound is the concentration here. So this is this. And the total is the free hemoglobin plus the bound. That's the total, right? Total is this. So we need to find what is the concentration of the bound form. And that we can define using the expression for Kd. Dissociation constant is equal to concentration of the free hemoglobin times concentration of the free hemoglobin times the concentration of oxygen raised to the power 4. Why? Because it's 4. And divided by the bound form. That's the dissociation constant, right? Very simple definition. So if you simply substitute that term, then in essence hemoglobin goes away. You end up with oxygen raised to 4 divided by Kd, 1 plus oxygen 4, oxygen, which is essentially equal to Kd plus concentration of L raised to 4, ligand raised to 4 divided by Kd plus concentration of ligand to the power 4. That's the Hill equation, right? Everybody agrees? Yeah? You have to say yes. Yeah. What is the problem with this? I'll give you a moment to think. What is the problem with this? Kd of second oxygen could be different from the first. Yeah, so in essence, that's a very good point. In essence, there is, you've heard about the term macroscopic Kd and microscopic Kd, right? Macroscopic constants and microscopic constants, right? So yeah, absolutely. What we are assuming for the time being is this is the macroscopic Kd, right? So that clearly is one issue, that when we are talking about 4 oxygens, you can definitely have different Kds, but in effect you can imagine that this is multiplied by the 4. But there is something else. There is something else that is.
So the Hill coefficient for hemoglobin is 2.8, right?
Okay, so practically, yeah. That's a very good point. Practically, yeah. So this N, for example, is, as we saw in the previous slide, is a measure of cooperativity. It is not a measure of number of oxygens that are involved, right? Yeah, okay. One more, yeah.
Is it because you don't have the concentration of hemoglobin in that final step?
Oh, is that a problem? No, it's not. Typically, well, you know, if you look at theta, and if you think of generally any protein, for example, myoglobin, the L is going to be 1, but not L. N is going to be 1, and therefore this is a traditional standard rectangular hyperbolic function, and therefore that doesn't really utilize the receptor concentration. So that's not an issue. But implicit in this expression, implicit in this Hill derivation or equation is the 4 oxygens. What does this mean? What does this actually mean in terms of how reactions happen? In terms of how reactions happen, what does this mean?
It's implying that it happens all at once.
All at once. It actually is trying to tell us that all 4 oxygens come together and they bind hemoglobin. How often does that happen? When you go from a bimolecular system into a termolecular system, that is much less probable. You go to a tetramolecular system, even less probable. You get this is a pentamolecular system. We are talking about 5 molecules coming together all at once. Extremely low probability, and therefore this is simply an expression to fit the data. This is not really a true expression. Okay. All right, so because we are interested in enzymes, I thought I would like to tell you a little bit about the Adair equation, which in essence tries to explain allostery and things of that sort. So don't turn off your mind simply because there are too many long equations. Okay, I'll go through it so that hopefully you understand and can appreciate that it's not very difficult. So here, for example, is a model of an allosteric enzyme that contains multiple subunits. Okay. And so here we have 4 subunits, enzyme E, substrate binds, and you get an ES1, where you have a conformational change in S in one of the subunits. As soon as ES1 is formed, this can generate kcat. This can generate product at a certain rate constant. Okay, assume. And this is the assumption that Adair used. So you get a product, and you can identify that. However, this molecule can also bind a second substrate and give you ES2. You can get this can also generate a product. And it turns out that for simplistic purposes, the value of kcat here is the same as the value of kcat here. So both function essentially at the same speed, essentially with the same catalytic efficiency. And the same thing happens. You get ES3, that can also give you the product, and ES4, that can also actually give you the product. What you can actually measure is some constant called K1, K1 standing for example, if you know a little bit about Michaelis-Menten kinetics, this would, for example, be the Km for the first step, the apparent Km. And this would be for the second one, and this would be for the third one, this would be for the fourth one. Okay? So we can, in here, what I'm assuming is that this is actually Ks and not Km. So if you're not sure about Ks and Km, don't worry about it. We are assuming it to be dissociation constant. So we can write the overall rate of reaction by combining all 4 catalytic enzymes, okay, all 4 forms. And that is the velocity of the reaction V is equal to kcat, which is this one, times the concentration of this, plus kcat times the concentration of this, plus kcat times the concentration of this, plus kcat times the concentration of this. That would be the overall velocity of the reaction. But then you had to multiply with how many different catalytic centers are present in each of these enzymes. So this would be twice as active as this. This would be 3 times as active as this. This would be 4 times as active as this. So therefore, you multiply it with 2, 3, and 4. Right? Got it? So what is the total enzyme? The total enzyme is obviously sum of all these different entities. So it's E plus ES1 plus ES2 plus ES3 plus ES4. That's the total enzyme. So if you want to find how much is percent saturation, then what do? We simply have to take, if you want to know about percent saturation, we simply want to take V divided by ET. That's what this is. But before that, we have to come up with the values, expressions for ES1, concentrations of ES1, ES2, ES3, ES4 in order to resolve this particular expression. We can get the concentrations of ES1 from that equilibrium, from that equilibrium, from that equilibrium, from that equilibrium, right? So that's what it is. So for example, K1 apparent, which is the macroscopic constant, this is the measured one. What we measure is concentration of E times S, concentration of E, which is all the whole thing, times concentration of S divided by this. That's the K1 apparent, right? Likewise, K2 apparent is therefore concentration of ES1 times S divided by this, and likewise everything else. Got it? All right. Now, it turns out this is the measured constant. Okay? This is the measured constant. But we are actually thinking about individual catalytic centers. And therefore, we have to think about the microscopic constants. So if we say that there is if we define the microscopic constant as K1, then K1, microscopic constant K1, is actually 4 times the macroscopic constant K1 apparent, right? Why is that? That's primarily because when the substrate S binds to a tetrameric unit, it can actually bind here or here or here or here. So in essence, the concentration, the number of catalytic centers are now 4 times. Effective concentration is 4 times. Therefore, the microscopic constant therefore becomes 4 times. So 4 times, so this is 4 possibilities for this versus only 1 possibility for that. Okay? Are you all with me? 4 possibilities for this. S can be here, S can be here, S can be here. So 4 possibilities for this versus only 1 possibility for this. Therefore, it is 4 times. So likewise, if you take ES2 and ES1, KS2, microscopic rate constant K2, is actually, there are 6 possibilities for this. You can have, this is 1 possibility. You can have this and this, which is a 2nd possibility. You can have these 2, 3rd possibility. You can have these 2, 4th possibility. You can have these 2, 5th possibility. You can have these 2, 6th possibility. Right? So there are 6 different possibilities, which essentially means that, to give you a physical picture, what it means is that if you have several ways, in which an enzyme can be recognized, it is easier for the substrate to find a site. Easier, right? It can quickly find it. That means less expenditure of energy, right? I'm not making a difference, am I? Right? I'll give you another analogy. An analogy would be if you're playing musical chairs, right? If you're playing musical chairs, so we have all these chairs and there's music playing, and then we are running around, right? Let's say there are several chairs that are vacant. Isn't it easier to go and grab a chair as soon as the music stops? Less expenditure. But however, if there are few chairs and there are too many people floating around, it's extremely difficult to find that one open chair, right? Something of this sort. So that's what is actually going on. That's why stoichiometry increases the effective affinity. Stoichiometry. So that's what we are talking about. We are talking about stoichiometry here. So in essence, did that help or no? Okay. So in essence, this is 6 different possibilities here and 4 different possibilities here. We already said this is 4 different possibilities, right? Therefore, the microscopic rate constant is 6 divided by 4 ES1, ES2, S in ES2. Okay, and you can extend the logic same time. This 4 different possibilities here, 6 different possibilities here. So K3 is 4 divided by 6. 4 different possibilities here, 6 here. And then K4, only one possibility here. There's only one way in which this can form. And then 4 different possibilities here. So therefore, this is 1 divided by 4, ES3. Okay? Yeah.
Can you maybe explain the difference between the microscopic and the apparent rate constants? That's where
Okay, very good question. So the simplest way to think about is that what is K1 apparent? If you were to take, let's imagine that this system was simply not there. Imagine, okay? Take it out of the system. Only this system was there. Then you would perform the reaction, you would measure the rate of the product formation, and you would fit it to an equation, Michaelis-Menten equation, and you would derive some Ks or Km, right? What is that? That's the measured, whatever, equilibrium constant or Km or Ks, whatever that you want to say. That's the measured one, right? But that's not the true constant. Why is that? Because of the phenomena that S can actually bind to the effective concentration of the subunits that can actually bind is 4 times more. So what you measure is not really the true, at a microscopic level, is not really the true constant. So you have to figure in stoichiometry. Okay. So you have to calculate this. Okay. After all, what you are interested in is so one way to think about microscopic constant is that, okay, so if for example you had just this system, only one, and that bound S and you got this, what would be the measured would be the microscopic. The measured and the microscopic would be the same. Because now you are really talking about atoms and those things binding together, right? And we are really talking about atomic level interactions, and that is what the Kd or the Km or the Ks that you're actually measuring. But when you have a system which is much bigger and it repeats, then the effective Km is not really individual interactions. And you want to know what the individual affinities or Km is actually be. That is microscopic. If it's still not clear, then what you should do is you should look up Cantor and Schimmel. Okay, I remember Cantor and Schimmel. I believe it's part 3. I should have that reference somewhere. Yeah, here it is. Okay, part 3. Obviously, this is a different page, but Cantor and Schimmel part 3 has a good discussion about the affinity of protons binding to EDTA, for example. Okay, so you have 4 protons, right? And therefore we kind of think that, oh, the pKa is going to be essentially identical for all the 4 carboxylic acids, but that's not true, and they are different. And you would think that even the first and the fourth would be the same, or the number 2 and 3 would be the same, but that's also not true. So it's a good discussion about understanding about what is microscopic and what is macroscopic. Okay, so yeah.
I understand the different combinations, understand is, why is there a factor of 6 by 4, for example?
Yeah, because there are 4 possibilities here and 6 possibilities here, or 4 possibilities, 6 possibilities here and 4 possibilities here. So you still have to figure out, it's not that one possibility remains true for all the situations. We are not really comparing that complex with this complex. If you were comparing this complex and this complex, then it would be 6:1. Right? So that's why it is. Can I go forward? Yeah? Okay, so in essence, we would like to transform what is measured into individual interactions, not interactions, but at an atomic level, at a molecular level, what is actually happening. So ES1 by rearranging, okay, so ES1 is equal to 4 times E divided by K1, and likewise all of these terms. And you can see that as you start, okay, so I have to explain this. So ES1 is equal to 4 times, so you bring this up here and then K1 goes down, 4 times E times S. ES2 is 6 divided by 4 times ES1, and you plug in ES1 from here. Okay? So that's why it is 6 times ES square K1 times K2. And then E3 is 4 divided by 6 ES2, ES3. So here you basically plug in ES2 from here, and then this one has ES1, so you plug in ES1 from here. So that's how you keep expanding. Okay. So for the time being, just assume that my thing is correct, because obviously this is published a long time ago. So ES3 is equal to 4 times ES cube, K1, K2, K3. ES4 is equal to ES4, K1, K2, K3, K4. Right? So that's how we have come up with these expressions in terms of the substrate concentration, which is something that we actually add and know in the experiment. And then K1 is the unknown. We don't really know, that we want to find out at a microscopic level what this is. So therefore, the velocity of the reaction, which is this, divided by the total enzyme, is equal to 4 times Kcat ES1, substituting here, 4 Kcat ESK1, ESK1 here. That's what this is, right? And then 2 times 6, 12 Kcat ES square K1, K2, and likewise. Yeah? For the time being, just believe that that's true. So this is 4, 12, 12, and 4. Okay? Remember, we are assuming Kcat is the same for all of these, which may not really be true. Okay? The reason why Hill fits so well is also hidden in here, the sigmoidal plot. So, now, what is the maximum velocity? Maximum velocity of the reaction is when you have all of the enzyme which is available to you, all of the enzyme that's available to you is converted into this complex. That's when you have maximum velocity, right? That's where that is. So in essence, and there are 4 catalytic centers in that enzyme. So therefore, the Kcat is actually multiplied by 4. So therefore, we have Vmax is equal to 4 times Kcat times Et. Okay? And therefore, if we substitute, if we take 4 times Kcat times the total enzyme, if we substitute, we get this expression. Okay? We get that expression. So this is S divided by K1. E goes, because E is common all throughout. So the concentration, just as in the last, Robert asked about hemoglobin, that's why E also goes, that's the receptor here. So in essence, you get S divided by K1, 3S squared, K1, K2, 3SQ, and likewise the rest. 1 plus 4S K1 and likewise the rest. So this expression, And V divided by Vmax is in essence percent saturation, is the equivalent to theta, that, right? So in essence, this expression is the full equation called the Adair equation. That takes into consideration the individual rate constants. The individual, not rate constants, these are equilibrium constants. Okay? The individual constants. Now, it turns out that for certain systems, because of the way, because of the values, the K1, the microscopic constants, that in essence, the dominant effect arises from K4. That's the dominant effect. That's the one that actually gives you the final rate. For most part, these contributors are not much. So although it is sequential, the effective K-cat is not good because of certain structure. And therefore, because S4 is such a dominant factor, that this approximately turns out to be equal to the Hill equation. And therefore, the Hill equation is a reasonably good fit, although not an accurate fit. And the K here is K1 times K2 times KT times K4, which simply means that as the system moves forward, this actually rapidly moves in the direction of ES4, although sequential. Okay? So, therefore, what we have here is the phenomena of individual subunits affecting the binding properties of the ligand so that it rapidly moves in this particular direction. That is cooperativity. Okay. So that is cooperativity. So starting with the first, starting with the idea of feedback inhibition and the idea of hemoglobin, came up with the idea that when you have molecules binding and they are binding at a certain site, the different systems can couple. So inherently, allostery, the word allostery doesn't invoke coupling, but coupling is implicit in allosteric phenomena. Okay? So that coupling could actually arise from the binding of one ligand and what happens subsequently to the same ligand. So it's, there is no additional different ligand that is involved, such as hemoglobin, oxygen. One oxygen is affecting the binding properties of the second, and that is called homotropic allostery. Okay, it remains the same. But obviously, we are interested in heterotropic allostery because we would like to have substrate, or we'd like to have another ligand being modified by something that we would like it to bind. So when binding of one kind of a ligand affects the binding of a second ligand, that's the heterotropic allostery. The principles remain the same. The phenomena essentially remain the same. But when you have heterotropic allostery, so all along, I know you might be getting the idea that what is needed for allostery is multiple subunits, right? That's the idea that I'm trying to convey here. But more and more, we have examples where you don't really need multiple subunits at all. You can actually have allostery with just one subunit. Okay? Allostery with just one subunit. And that is pretty phenomenal because that means that we can design regulators. We can actually modulate. So heterotropic allostery, this is very old example, aspartate trans-carbamylase aspartate system. So this is a classic case. If you are interested, read up on this heterotropic allostery. So once again, you can have allostery. This is the classic case of hemoglobin versus, myoglobin versus hemoglobin, where you have a linear scale here. And then the allosteric enzymes, you can have allosteric inhibitor or you can have allosteric activator. Okay? So you can have either. It doesn't have to be inhibition. It doesn't have to be allosteric inhibition. Allosteric inhibition is actually going to make it even more sigmoidal. An activator is going to activate it, change the sigmoidal characteristics. So here's what I was trying to describe as to what the different K1s could be. For example, for hemoglobin oxygen system, in the absence of sodium chloride, the first K1 is 8.8 millimeters of mercury. The second one is 6.1. The third one is 0.85, and the fourth one is 0.25. So you can see that as you progress from K1 to K4, the affinity kicks in. The difference here is approximately 30-fold difference. So that's pretty phenomenal. And therefore, you can imagine that after some time it rapidly moves in the direction of this, which is why you can easily fit it to the traditional Hill equation. And then likewise, in the presence of 0.1 molar sodium chloride, which is reasonably physiologic, slightly less than what we have in our system, the difference between K1 and K4 is even more dramatic. Okay? So clearly that's that is called positive cooperativity, when the binding of one molecule increases the affinity for the second molecule. That's called positive. It's aiding, it's helping. You can have actually negative cooperativity, right? Under an extreme condition, the negative cooperativity would be that binding of one molecule doesn't make the second molecule bind at all, which simply becomes a uni-uni system. Okay, that's an extreme yeah.
What's the cause for the 5-fold difference in the K1 in the presence and absence of sodium?
Oh, what's the cause? I don't really know structurally exactly what's the cause, but there are some structural changes here, obviously. We have Dr. Safo, who is working. We don't have him here right now. He was here. But you know, he is the one who has contributed to the development of a molecule that effectively changes these. A molecule that almost made it to the clinic, that could have been used by athletes, because it reversed it. So it disfavored binding of the oxygen, so that if you take it, you release a lot of oxygen. I think so. And so he designed a molecule that changed the equilibrium. I wish he was here. He could have answered the question. But yeah, I mean, he's done a lot of, he's a crystallographer, so he's done a lot of structures. But you can ask him. He might come back. So negative cooperativity. So we might think that negative cooperativity is not possible. We might think that, you know, that's something unusual. Binding of one molecule would disfavor binding of the second molecule, but then why would the second molecule try to bind in the first place? Well, there are some really nice regulating features that arise from the system. And I have a simple profile. This is a very generic profile for you to understand, and you might actually see this reported in literature. And if there are curves of this sort, you can infer pretty easily. For example, on a linear scale, both linear scale, you have this is our traditional, the blue line is our traditional rectangular hyperbola, where the cooperativity n is equal to 1. Okay, no cooperativity. And then as you increase, as you slow it down and then suddenly increase, which is the green line means it is more cooperative. It is positive cooperative. Okay. So the affinity increases as more multiple molecules bind. And then the red line, which goes on the other side, is negative cooperativity. Okay. So the differentiation is very easy, the identification is very easy if it is positive cooperative. Identification is easy because it's a beautiful sigmoidal plot, easy to identify. But when it moves from positive to negative, you really have to be careful, and it's not absolutely easy. For most part, many people simply fit this to rectangular hyperbola and never infer it. Everything basically goes in the error bars, error that typically arises from experimentation. But you have to be careful. Okay, so how is allostery manifested? I gave you one example, which is what is described here, which is in essence structural mechanism. We tend to think about mechanisms that are based on structure, right? This is a mechanism which is also called the induced fit mechanism. Actually, induced fit terminology came up because of Daniel Koshland's work. He proposed induced fit mechanism. An induced fit mechanism essentially implies there is a structural change. A fit is induced into the system. A better fit is induced into the system. So binding of an allosteric effector induces a conformational change, really a structural change in the ligand. So a new structure is induced. And you can think of both activation as well as inhibition phenomena. Both of these are equally possible. So for example, in this particular case, you have an enzyme and you have two sites, and you have, once again, we are now moving into monomeric systems. So I think in terms of regulation, this is more relevant for us. So an enzyme has two sites, substrate binds, you get a product. When you have an inhibitor that binds in an alternative site, an allosteric site, there is really a significant structural change that happens that disfavors binding. That is inhibition. Very easy to understand, not difficult to appreciate. Likewise, for activation, you might actually have an enzyme which, for most part, on the native state, doesn't really convert a molecule, a substrate into the product. Why? Because the binding site is not formed. You have several different zymogen forms and things of that sort that can prevent the reaction. However, a molecule can bind an allosteric site, form this active site, and generate significantly higher products. That is activation. Both of these phenomena are induced fit, primarily because we are invoking significant structural change. The key is significant structural change. That's the key. That's the easiest thing to think about in terms of allostery, and was always thought of in terms of allostery, that this is how things work. This is the minimum requirement. Structural change is the minimum requirement. Well, more traction is gaining ground with this concept. And this concept is the conformational selection mechanism of allostery, also called pre-equilibrium mechanism of allostery, also called population shift mechanism of allostery. Okay, so all of these are essentially the same thing, used by different people, but meaning essentially the same thing. So what is happening here? So A here is the induced fit. So let's just revisit induced fit. So these are, for example, the electronic states or some state description in terms of the structure of the molecule. And the molecule, the receptor may exhibit a primarily ground state phenomena where one of the conformations is stable and the second population is not as stable. So this is the most favored one. When an effector binds to the macromolecule, you have considerable reorganization such that now this becomes the most favored state. That's the significant change that I'm trying to invoke, which we saw earlier. So this is the induced state phenomena, a dramatic change here. Okay. However, a molecule can actually exhibit, in here, the population of this is significantly higher than the population of this form, to the extent that this may not actually be present under the conditions of the experiment. The Boltzmann distribution might actually significantly favor this, and this may not actually be present at all. However, a molecule may exhibit several populations, and just two are indicated. Both of those are actually present. Okay? Both of those are actually present in whatever experimental condition. So what happens when the effector binds is that it changes this equilibrium in the direction of the bound form. And because of this change, what happens is that it pulls it. For example, if we have four different populations of the macromolecule, the ligand binds only one of them, and it drags the equilibrium in this direction. Eventually, there is a readjustment of this equilibrium, and the formation of the complex is reestablished, which is called dynamic equilibrium, right? That's the conformational selection. This conformation is selected preferentially, or pre-equilibrium is disturbed. There exists an pre-equilibrium between all of these, and that is then moved forward, or there is a change in population shift. So all of these terms are essentially the same thing. Okay, clear? Now, this is a phenomena that is being discussed even more recently, that you may not actually need a structural change in order to exhibit allostery, that you may not need different conformations to exhibit allostery, that you may only change the proportion of movement of different segments in the macromolecule. Okay? So that is called basically a dynamically driven mechanism of allostery, or entropically modulated mechanism of allostery. So what is being invoked is that simply entropy is changing, enthalpy is not changing at all. We had a discussion yesterday about delta H and delta S, right? So in essence, what this means is that, and this is C, what this means is that you have this, the macromolecule in some state with certain entropy, and then you have essentially the same macromolecule with certain entropy, except that there is an entropic exchange. So if you look carefully, this goes a little bit more on this side, whereas this goes a little bit more on this side. So it's an entropic exchange. So if you can imagine, if you have a macromolecule, the effector ligand binds here, and at that point in the macromolecule you have this thing moving around like that, okay, and then this molecule binds here, so it tightens this up, and therefore the entropy around here also changes. So there is an entropic exchange going from one side to the second side. No major structural change, right? No major structural change, no significant population difference, and yet there is allostery. Okay? Yeah, are you all with me? Okay, to give you a physical picture, keep the physical picture in mind so that it becomes easier. Yeah.
So what contributes to the entropy? Is it like rotation, vibration, transmission? Like there should be increase in entropy so that system is favorable, right? It
Yeah.
cannot decrease.
Yeah.
According to that gives free energy theory. So you mean there is increase in vibration, or like in physical, what's going on?
So the way in which, if the macromolecule is vibrating quite a bit, remember that the entropy of the system has to increase. Right. The entropy of the system doesn't just mean the macromolecule. There are water molecules that are floating around, and we saw a discussion yesterday. So it's way more complex. But in terms of, and I have a slide to hopefully to tell you a little bit about. I just noticed that I'm already too slow. So So, in the macromolecule, if you have one side, one segment is moving fast, and when it is locked with an effector, that segment might actually slow down. But then it opens up the other side just a little bit without major structural change, so that another molecule can bind fairly easily. Okay? So it's an entropic exchange, whereas this one was, for example, tight. Now, because of the binding of this opens up a little bit, and you have, so when you have an opened up a little bit, essentially means that you are exchanging entropy. As far as this system is concerned, the overall entropy has to increase, absolutely. Yeah.
So, if we think about it without any structural changes, without any sign opening up, regular state, we have protein ligand binding, which should be entropically. So the thing is, you need to rigidify both your ligand and your protein. So what if an effector binds the protein, rigidifies the protein? So you don't have this penalty anymore when you're making your ligand-protein interaction. So now the ligand-protein interaction after the effector binds is more entropically favored. So can this explain?
Yeah.
You don't have to have any structural changes, but you're getting rid of an entropical penalty when you're ligand bound, because now your effector is actually rigidifying.
But when the system works to give you the complex, it's the overall entropy of the system, right? So if you can hang on to hopefully thrombin case, I'll take 15 minutes. Hopefully I'll be done then. I'm already on 12. Oh my gosh. Okay, we'll see how far we can go. So how do you detect entropy? Okay, the question is obviously we have especially when the difficulties arise when there is no major structural change. Right? Obviously, one of the major ways in which what did I say? One of the major ways in which allostery can be detected is structural change, right? And more and more systems are being discovered where there are no major structural changes, right? There are no major structural changes, and therefore it creates a problem. You might have the enzyme, and then you might have an enzyme inhibitor complex, and the enzyme inhibitor complex and the enzyme, no structural change, and yet when you actually do the reaction, there is inhibition. So clearly, how do you detect? Especially for GAGs, this is fairly useful, and this stems from some of our work, which was done a long time ago. So we can actually use kinetic methods. Okay, kinetic methods are fairly useful. So one of the ways in which you can detect allostery is structural change, crystallography. Another way is, for example, Phil might say, well, you can use molecular dynamics. Definitely, that could be definitely used. Another major way, for example, Project 3 people are using NMR, two-dimensional NMR. I think it should be very easy to detect. So, yeah, you really require significant structural change. One of the ways in which allostery can be detected is using kinetic methods. So and this is rapid kinetics, okay? This is not our traditional kinetics. This is rapid kinetics. So we typically can use, for example, stop flow instruments to detect. So under traditional case, where, for example, there is a one-step process, the overall rate of a reaction is typically described by K off plus K on times the concentration of the ligand. Forget about derivation of this equation, but for the time being, just accept it. Allosteric processes, for most part, are two-step processes. We already said that, right? It's sequential for most part. So if you think about a simple system, and this is a monomeric enzyme, this is just one chain. So the enzyme can actually bind a ligand, and you can get a complex in the first step. And this complex can actually undergo some kind of a change, whatever change that could be, small change, large change, whatever that is. Majority of the cases when this happens, this is an induced fit process. So this is a significant change. Starting from E to E star is a significant change going from this particular route. And what happens is that this process is typically described as the induced fit process, the IN process, which is allostery as described by A. But there is another phenomenon. So when you have something like this, the observed rate constant for this process under rapid kinetic state is described by this kind of a phenomena. It is a hyperbola. It's still a rectangular hyperbola. And K observed is directly proportional to, for example, the ligand concentration. And what you get is something like this. Okay? What you get is something like this. So this is an induced fit process. However, if it is pre-equilibrium, which essentially means that the enzyme is in equilibrium with an altered form, slightly different from. If there is pre-equilibrium, this is a population shift, and the ligand binds to that altered state and gives you this complex, then this process can be very easily detected. And that process is K observed is pre-equilibrium is something of this sort, and there is a good derivation for that. The observed rate constant here, for example, is not directly proportional to the ligand concentration as in the induced fit. But the observed rate constant is essentially indirectly, inversely proportional to the ligand concentration. So what happens therefore is that the expression, that the profile goes completely opposite to the induced fit process. So therefore it is fairly easy, and this dramatic change is easy to detect, induced fit versus pre-equilibrium process. Okay. The entropic processes require further investigation. Now this is actually true. We might think that this is difficult to detect, but this is actually true. And what I'm about to tell you is that we might think that a protein or a receptor is the one that determines whether it is allosteric, positive, negative, whatever the case is. So that is not the case. So here's antithrombin, a molecule that we all are interested in. And this is actually heparin oligosaccharides. So this is how the rates are measured. So we typically do fluorescence, and what we are going to discuss is fluorescence in terms of studying of interactions. And you measure as a function of time. So this is extremely rapid. So we are really talking about reactions that occur on sub-second time scale. And this is one of the ligands, for example, at different concentrations. And you measure the rate. So this can be fitted to the exponential processes, exponential expression. In this particular case, I think I'm showing you for this profile. So there are two rate constants. So this is not a single exponential. This is a double exponential. And let's not forget, let's not discuss as to why that is single and double, but just accept that that is double exponential. So for a molecule of this sort, which we all recognize as the key constituent of heparin, as the concentration increases, the rate constant increases, and you can clearly see that it actually tends to saturate at a certain concentration. Saturation indicates a two-step phenomena. So going back, I didn't present the one-step thing. So for a one-step process such as this, you actually keep getting increased rate constant as you keep increasing the ligand concentration. Okay, so it's a linear profile. Here, this is not a linear profile, it tends to saturate. Therefore, this is a two-step process. And because it's a two-step process and the rate increases and it tends to saturate, very similar to, for example, here, it tends to saturate. So this is what we have measured. We haven't really measured right up to this. It goes beyond the instrument. So therefore, this is an induced fit phenomenon. So actually the key molecule that activates antithrombin induces an appropriate fit, which is this whole thing, 5 residue sequence. But you eliminate just one of this, just one residue. What happens, the same target, same antithrombin, you suddenly start seeing a completely different phenomena where the rate goes down. There is a reason why there is a second component built into it. There are two changes that are actually happening. And therefore, this is the pre-equilibrium pathway. This is the population shift pathway. So while one of the molecules is able to induce a fit, another molecule is not able to induce a fit, and it's for the same target. So that's really the key. The molecule, whatever thing that we decides what kind of a process does it choose. It's not the receptor that chooses what mechanism. Now, in terms of the design, this actually can be very useful. For example, this is the crystal structure of antithrombin, something that you have seen quite a bit. And it turns out that the 3 residues that actually induce a fit are just these 3 residues. And 2 residues that do not induce a fit are these 2 residues. And they help select a particular conformation. So really, an allosteric effector, the type where you have 2 molecules playing a role, and the catalytic center is somewhere here. This is the business end of the molecule. And this is the allosteric end. So this is the business end, and this is the allosteric end. So you could actually have 2 molecules and 2 residues and 3 residues actually working simultaneously, independent, and not just 5 residue sequence playing a role. Okay. All right, allostery also. Okay, so 5 more minutes. So allostery also plays a major role in targeting other coagulation enzymes, and this is also a slide that I presented last camp, and many of you might have seen this, but we typically don't think of this mechanism and allostery, but here allostery is built into the system. So this is what I described. This is the 5 residue sequence binding to antithrombin and effecting a change here. Now this is not really true in strictest sense, but it's good to understand, and it's good to think. So this is the allosteric process that I alluded to, but there is another allosteric process that also plays a role. For example, for thrombin. So this is allosteric, but at the same time, binding of the heparan species to an exocyte on thrombin also induces a change in the active site. We don't fully know how much of a change that is, but even this is allosteric, just as this is allosteric. So the entire system is allosteric, and that is phenomenal for design purposes. That is phenomenal for regulation purposes. And that actually holds true for factor 9A. That also holds true for factor 10A in the presence of calcium. So in the presence of calcium, it's basically the same thing. So it's a dual allosteric process. And factor 10A, factor 9A, thrombin, these are obviously coagulation enzymes, but it turns out that this process is essentially common across the board. Nature uses this throughout allosteric design. So here, for example, is an illustration of what happens in terms of, so this is the acceleration. Okay, so just for those of you who have not seen this, so what happens is that heparin binds to antithrombin, that generates a complex, and then this complex reacts with the enzyme. In the presence of heparin, the rate is dramatically increased because of the formation of this ternary complex. Okay, so if you take the rate constant for the formation of the ternary complex versus the rate constant for the formation of the binary complex, which is just these two, no heparin, the ratio of those two rates is the acceleration, okay, is the acceleration. So that acceleration is being plotted here. So this acceleration is being plotted here. So we have several different enzymes, all essentially belonging to the coagulation cum inflammatory system. And K is kallikrein, APC is activated protein C, P is plasmin, and then TPA is a tissue type plasminogen activator. And we are finding how well these enzymes are inhibited by antithrombin when it is binding to 5 residue sequence, when it is binding to 26 residue sequence, and it is binding to 50 residue sequence of heparin. So this is heparin with different chain lengths. So if conformational allostery, induced fit allostery, was the one that was active, then we would see acceleration only with 5 residue sequence. If population shift and or entropic shift allostery was effective, then we would see some changes in these two, in addition to H5. Okay. So this is acceleration, and you can see that this is in folds. So this is 1,000-fold, for example. Well, actually, even this one or this one, which is 2-fold, essentially means 100% change. So we are really talking about dramatic increases. Even this one is significant change. Percent change even here is significant. Imagine what's out here. So as you go, for example, this is really small, hardly any change. It's about 1.74. So it's 70% increase here. So as you go from H5 to 26 to 50, the allosteric contribution is pretty huge. It's about 2,000-fold. Likewise, if you see for 10A, significant increases. For 9A, these are the three that we saw in the last slide. Then 11A. 11A really requires much longer chains. 26 is not good enough. And 12A. So all of these are coagulation enzymes, and nature has engineered. There is a differential chain length dependence. So we don't really know exactly what is really going on here. Much work needs to be done. But at the same time, you do see some changes here. Now this could be stoichiometric, the one that we discussed, because there are multiple sites, it's easier to find, so the concentration increases, therefore enhanced change. So this could partly be stoichiometric because it's not as dramatic. And therefore allostery really plays a significant role in inhibition of several coagulation enzymes. This could actually be true for several other systems. Okay, so continuing from our first part. So we wanted to discuss thrombin allostery. And thrombin allostery is even more subtle than antithrombin allostery, obviously. Thrombin is really an important enzyme for coagulation, not only for coagulation, for several other things. And in order to regulate numerous processes that it plays a role in, it has several different sites. One of them is obviously the catalytic site. This is where the peptide substrates bind and they undergo hydrolysis. In addition, it has, for example, a site that is approximately 20 angstroms in this standard sort of view. This is called the standard view. On the right hand side, 20 angstroms away, we have an exocyte 1. Earlier it used to be called anion binding exocyte 1. It actually binds anions. And then on the left hand side, we have approximately 20 angstroms away, we have exocyte 2. Exocyte 2 is also anion binding exocyte 2. So both of these bind anions, and yet they can differentiate really, really well. Exocyte 1 binds anions that are substantially hydrophobic. Exocyte 2 binds anions that are essentially significantly anionic. So the anion density of ligands that bind here is significantly higher than the anionic density of ligands that bind here. And then there is a sodium binding site, which is approximately 10 angstroms away from the active site, and sodium binding converts thrombin into a more active enzyme. Converts thrombin into a more active enzyme. So sodium is an allosteric activator of thrombin. Okay, so these are the 4 different sites. In addition, there is supposedly a hydrophobic site, which is somewhere close to here, which binds hydrophobic molecules. That includes aromatic hydrophobic molecules that typically bind there. Exosite 2 is involved in binding heparin and chondroitin sulfate, and both of these molecules are important for our PEG. In fact, majority of people here, especially the trainees, they are working on chondroitin sulfate. Like you built the library of chondroitin sulfate disaccharide yesterday, and chondroitin sulfate binds in exosite 2. Chondroitin sulfate is actually present on thrombomodulin, and thrombin-thrombomodulin interaction is involved in an anticoagulant effect. Heparin thrombin interaction is involved in procoagulant effect. So they are two similar enzymes, and yet they are involved in differential regulation. That arises because of several other features. Glycoprotein 1b alpha is a molecule that is interesting because it binds both exosite 2 as well as exosite 1. So this is one molecule that binds both. Exosite 1 is a site where, for example, hydrogen binds or pyridine binds, and this is something that some of you may know of because this is a drug. Pyridine is an anticoagulant drug, and it's an approved product. Thrombin binds in exosite 1 PAR1, which is involved in coagulation as well as inflammatory processes, and it binds fibrinogen or fibrin and thrombomodulin. So in essence, this is a fairly complex enzyme, and it's possible that all of these sites are linked. We don't really know. So we really have phenomenal complexity here, primarily because each of these sites may be allosterically coupled, and that's the interesting part. So thrombin keeps shifting, and there is an intense discussion about whether there are structural differences when sodium binds thrombin. In the absence of, so I have not included here thrombin which is bound to neither of these. Okay, so that's another feature. But so whether there is thrombin, and that the thrombin that is unbound, that is not bound to sodium, has a different structure, and there is an intense discussion going on in that fashion. Numerous structures. There are close to 500 different structures of thrombin published. Many of the ligands are exosite 1 ligands, some of them are exosite 2, obviously numerous inhibitors bound in the active site, and then several structures, like tens of structures in which sodium in different form and mutations and potassium and lithium and those kinds of things. So it's a richly studied enzyme, especially from both site-directed mutagenesis as well as crystallography. So I'm simply jumping ahead because there's just too much discussion, and what I'm showing you here is that the current view is of conformational selection. So thrombin is currently viewed, and this was just published, so as of conformational selection. And although, let's see if I can turn down the lights. I think this should work. So if you look at these, so what is being shown are the structures of different forms and different forms of thrombin, and I want you to tell me as to what differences do you notice. Okay, so for example, this is PPAC. PPAC attacks the active site. So this is active site inhibited thrombin. This is just plain thrombin. And then with sodium, this is that. This is exosite 1 bound. Then when this is bound to sodium, you get this structure. Or when with sodium you bind hydrogen, which is exosite 1, you get this structure. And with PPAC, this structure. And this is hydrogen plus sodium. This structure is hydrogen plus sodium plus PPAC. So all of these together. So there are 3. Okay? So you get the overall picture. And what I want, and I know it's too small, I want you to think about what differences do you see? So this loop, I'm not pointing out difference, I'm simply telling you, this loop is the same as that loop, okay? You cannot see this loop because hydrogen is bound here. And these are all crystal structures. There's essentially no difference between any of these forms. Nothing. Practically nothing. But there is a difference. In terms of R factors, there is a difference. So if you really look, so what they have done, this is Jim Huntington's paper. So what he's done is that he has in essence plotted how variable are the different segments of the molecule is, and that is color coded. So this is a sort of heat map thing. So if you can see, as you move from completely free thrombin with significant variations, as you move to different ligands, effector ligands, you're actually seeing significant reduction in the movement. And therefore, one of the forms is actually becoming more and more stable. And it's reducing gradually the entropic factors. That's the current view of allostery in terms of thrombin. That whatever is actually happening is simply happening because the movement is going down, because it's stabilizing, because there is an exchange. Everybody with me? Yeah? Obviously, we have discussed quite a bit, so I think it's easy to appreciate now that we have had that good discussion, but this took decades of work to figure this out. Still, there is one important thing that is completely missing. Nowhere in here is the structure of exosite 2 bound thrombin. Okay? Although exosite 2 is known, the structures are known, heparin and is actually studied. So, and yet, so for most part, people even today believe that exosite 2 is not really coupled with the active site, and or exosite 2 is not coupled, exosite 2 is not really coupled with the active site, and or exosite 2 is not coupled with exosite 1, and exosite 2 is not really coupled with sodium binding site. So all of this is a big question mark. And for us it is interesting primarily because heparin binds in exosite 2. So all of the work that I presented, allostery arising from this beautiful mechanism arises because of binding to exosite 2, and that doesn't figure into all of this work. Obviously, as some of you know, that we have published, exosite 2 does really allosterically modify thrombin. It's just where you hit. So what molecule, going back to the argument that I made, what molecule is it that that plays a major role in defining whether it is induced fit or ensemble or dynamics. So now just to leave you with this thought, that allostery actually plays a role across the board. Okay, so I'm trying to generalize now even more. going away from the coagulation system. So allostery actually plays a role across the board. It's just that we have not studied, especially with GAGs, that this is completely open in terms of trying to understand mechanisms and then trying to utilize these regulatory features for the purposes that we would like to do. So angiogenesis modulation, for example, angiogenesis arises because of growth factors that play a role, and then growth factors bind the receptors, it is believed. So there are several different models, and I'm just presenting one of them. I believe this is coming from, I think this model is coming from this paper. So this is just one of the models. One of the models says that the receptors dimerize. So they were separate, then they dimerize. They dimerize not only because the growth factors dimerize, so the growth factors have to undergo dimerization, but that is assisted because of the heparan sulfate chains that are actually present on these cell surfaces. So this is the proteoglycan, has a heparan sulfate, and that brings together these things. So you can immediately imagine that binding of heparan sulfate induces a structural change into structural and or ensemble change into the growth factor that assists in this dimerization process. Significantly allosterically driven, yet we don't really know how much of this is true, and can we really exploit it, or can we really intercept this process. Either way, angiogenesis inhibitors and or angiogenesis activators, either way, for our purposes. Likewise, there is a strong possibility of regulating viral entry, and I'm showing this only for herpes simplex virus, but it's actually true for essentially all enveloped viruses, HIV, dengue, all of the viruses. They utilize to significant extent. There is a similar mechanism. So the way that this works is several steps, but the way that this works is that these viruses typically have glycoproteins, and I think Phil mentioned glycoprotein D in his very first slide yesterday. So glycoprotein D is also present here, for example here. But there are these glycoproteins, and each of these are heparan sulfate recognizing elements. So you can imagine what is actually happening. The target cell has heparan sulfate proteoglycans, and these are actually floating around. So what you have is basically an attracting process. So the heparan sulfates are floating around, and they are highly negatively charged. So the glycoproteins have heparan sulfate binding domains, or to a certain extent reasonable charge density or positive charge density. So the virus is actually floating around, and the heparan sulfates are moving, and that engages them to begin with. Okay, so that's the catchment area in essence. So these utilize this process, and then because of certain types of interactions that are not very specific, the virus rolls down. So it actually walks, very similar to what we saw in there. So virus actually rolls down, and it reaches pretty close to the surface. At this point, there are several other receptors that come into play, including a specific sequence on the heparan sulfate, which has a 3O sulfate. So these are the gatekeepers. These are the ones that actually filter. Well, do we want to take it in, or do we don't want to take it in? So if GD is bound, if GD is found, then it recognizes this sequence. It also recognizes these receptors, and the virus is internalized. So this is the mechanism for virus entry into cells. You can imagine that most of these processes are allostery driven, which means that it allows us to hopefully intercept these processes based on, for example, structural features of the heparan sulfate. So there is phenomenal potential in terms of really understanding allostery and then trying to utilize it for regulatory purposes. So not only that, essentially all trypsin-like coagulation enzymes, trypsin-like, so these are trypsin-likes, for example, but all trypsin-like, including trypsin, is an allosteric enzyme. Chemokines, IL-8, GAG binding, allosteric. Other serpins, protein C inhibitor, allosteric. Now in this So it almost appears that allostery is fairly common, especially for GAGs. It's just that we have not appreciated enough, which is why I think I wanted to talk about this in first place, so that you can keep this in mind while you do the work with GAGs. And therefore, it presents phenomenal opportunities of discovering modulators for essentially everything: inflammation, coagulation, cancer, angiogenesis, things of that sort. Okay, so with that I stop on allostery. Questions?